I will also start recording. Okay, so I will admit all, and I will disable the waiting room as well. Okay, so good morning to everyone, and so we are ready for the third seminar of the SPS webinar series, and so I can see the participants are still joining. So let's wait another 2 to 3 minutes. Hello, good morning to everyone, and I'm Dr. Chami Redusuri. I'm the staff advisor of the IEEE Signal Processing Society Student Branch Chapter of the University of Moratuwa, and we are in the third seminar of the Signal Processing webinar series. So today our speaker is Mr. Jathushan Rajasegaran. And so if I give a brief introduction about Jathushan, so he received his BSc in Electronics and Telecommunication Engineering from the University of Moratuwa in 2018. Actually, he's one of my students, and I was the co-supervisor of his research project. Following his undergraduate studies, he spent 2 years at the Inception Institute of Artificial Intelligence, UAE, working on continual learning, meta-learning, and few-shot learning. I think with the supervision of Dr. Salman Khan, right? Yeah, not the actor, but yeah, this is a different Salman Khan. Okay. So, and after that, actually, he was accepted for the graduate studies in many universities, including MIT, Stanford, Berkeley, and everything. And he joined the University of California, Berkeley, and he's currently a first-year PhD student at the University of California, Berkeley. His research interests are mainly in learning methods for deep neural networks. Actually, the recent trends, including the continual learning, meta-learning, and few-shot learning, and especially the 3D vision. So I would like to invite to the Mr. Jathushan Rajasegaran for his presentation, and he informed me to actually mention that if you have any question, you could actually ask in the middle of the presentation, or actually we have the platform. I think the Bhavan has shared the link Slido. So if it is a disturbance to the talk, you may put your question in that platform Slido. Then at the end of the presentation, we would forward this as much as all of these questions to the Mr. Jathushan, and also in chat, I think Bhavan has sent to the link again, Slido and the code as well. So I'm really glad that I can listen to actually the webinar of one of my students, and so I'm really happy person today. And so I would like to invite Mr. Jathushan Rajasegaran for his insightful seminar. Jathushan.
Thank you, Dr. Chamira, sir. And first of all, I would like to thank Dr. Chamira and the Signal Processing Society for inviting me to this talk. Thanks for inviting. I'm really excited to talk with you guys about this. Is most about like my past research, but really excited to share with you. And so this talk is more about meta learning. So this is sort of like a new topic, and how these meta learning can be sort of connected between continual learning as well as future learning. So these are the three main topics we will discuss today: meta learning, continual learning, and future learning, and how each of them can be connected or interconnected between what are the basic relationship between meta learning and continual learning versus meta learning versus future learning. And we will discuss the definition and how this can be extended to high levels. And as Dr. Chamira mentioned, like feel free to stop me at any point and ask question. I'm really happy if you can stop me at any point. That will be more organic. Feel free to ask any question at any point. I would like this talk to be more like a discussion oriented, because the topic is more or less like a technical talk. So it would be great if you can just ask any question at any point of time. Okay, so sir is already mentioned, but hi, I'm Jathushan. So some of you know I'm also from ENDC, graduated from 2018. And although I'm really interested in photography, I don't have a good photo of my one. This one, I'm using the same photo for like 6 years. This is from ENDC one. And I'm currently first year PhD student at UC Berkeley. Yeah. So just let's start with a movie. Can you see? So, okay. So this is from 2009, sorry, 1927 movie. This is called Metropolis. So, okay. I'll stop for a while. Okay. Hope I think you can see that one, right? Okay, so this is from 2019, sorry, 1927, movie called Metropolis. So people say this is the first sci-fi movie ever created, and this is about like some people trying to create machines and create an artificial intelligence. This girl is like a AI robot. So this story is that we have started with like very huge expectation in like 90s, early 90s, like how the AI is going to be. Like people have thought of like it will change the world and it will create like robots will take control and so on. But so actually that's what created this something called AI winter. So that means in 1990s people are sort of fed up with this one. It's not working at all because the main problem was the data in and computation. Because in 90s we don't have enough computation as well as there is no enough data to learn meaningful representation. So, but back in 2010s, people started using very like powerful computing like GPUs as well as the power to create more rich data. So in like 2013, when the AlexNet was published, so it sort of kickstarted the deep learning era. So and there was this ImageNet data set also published around the same time. So ImageNet has like millions of images, right? So ImageNet has like millions of images, and so people have spent a lot of time to label these images. Like you have this image of a chair, you have to label these images. But like there is this famous saying, like a picture was like 1,000 words, right? See, we cannot just simply label a single image with a single label. So that's one problem. And doing that sort of labeling requires lots of time, and it takes lots of power or money to create this sort of data set. Okay, we have this imaginary data set, but that's a sort of a tip of the iceberg. In the internet, there is like millions of images without any labels. Okay. Yeah, so and also sometimes it's very hard to label this. It's impossible to label all the data we have, right? So if you take internet, there is like millions of images every day uploaded to the internet, and most of them does not have any label. So it's very difficult to have a very good quality. That means the correct label as well as with the label to have this sort of data set. So that's the problem we have. Like at the start, we had this very good supervised learning. We have an image and one single label. That's fine. But when we have this different data available to us, we have to modify our learning setting or learning theory to such that to accommodate the available data to you fully potentially use this available data to us. So that's where this different sort of learning setups comes in. So like, okay, so like this is just a simple ImageNet example. We have like millions of images, and we each of them has like labels. We can simply train, but that's not just a simple. That's not just the solution we have, because okay, so there is this sort of a funny example that it's called Licon cake. Hope most of you know Jan Licon. So he's sort of the inventor of convolutional neural networks. So he says that if you take a cake and the cake of the cake is actually similar to unsupervised learning. That means there is these millions or billions of images without any labels. We can use them to learn this unsupervised learning. The icing is somewhat similar to like supervised learning. That means there's a small amount of uh, data available with labels, which is very small compared to the cake. Icing is very small compared to the cake, and there is this cherry on top of this cake. That means it's like uh, very small reinforcement. That's a bit of a controversial part, but if you can think of, there is this different set of data, and according to that we have to adapt our algorithms to learn meaningful representation from this data. So if you just think about this, lots of deep learning inside the deep learning, we have like supervised learning. So supervised learning is most of you know, like we have the data and as corresponding label to this data. And then we have unsupervised learning. That means there is no data at all. Sorry, no label at all. We only have the data and we have to learn some meaningful, we have to understand or learn some meaningful representation of this data. And in the middle ground, we have semi-supervised data learning. That means some part of the data has label and some part of the data does not have any label. And then we have self-supervised learning. That's like an interesting topic to me. That means there is no label available to this data, but we learn some supervision from just the data. I will talk about this later also, but that's a really interesting topic. We use this image as a supervision to this learning problem. And then we have this online learning. So most of these all the supervised and supervised learning have this assumption that the data is IID, that means independent identical distribution. But that's not always true, right? Sometimes for day one, we have, like, if you take maybe like finance data or something, or like temperature or the climate data, the distribution is going to change every time. So that's online learning. So how we can develop some algorithm which can learn from this non-IID data. And there is this transfer learning. We have this, so we learn from one set of distribution of data and use this knowledge to transfer the knowledge to learn a different set of learning, like learn some meaningful understanding of a different set of data, which is it has a different distribution than what is trained on. And we have this continual learning. We will discuss more in depth later, but the continual learning means like the data comes like every day we have a new set of data, but we need to learn continuously. We need to learn this from incoming data. And then we have future learning. That future learning means we have a very small amount of samples. That means, like, usually these deep learning networks it requires a large amount of samples, right? Millions of images and labels. But future learning sort of tackles the problem where we don't have enough data or samples, or like 1 or 2 samples per class, and how we can effectively use these samples to learn a good classifier. So this is like sort of this big picture of like what sort of learning algorithms we have for different set of data distribution like we use to interfere. So this talk is mostly focusing on these two topics, the continual learning and future learning, and how we can find somewhat good middle ground between them using a meta learning. So that's a big picture of this talk. Uh, if you have any question, please feel free to ask at any point. Okay. So let's start with continual learning. So usually what we have, okay, let me, okay, okay, I think you can see. So think of continual learning as learning non-IID samples. That means IID means all the sample from the same distribution. Non-IID means for a different time, we'll have a different set of samples, different distribution. So day one, I need to classify cats versus dogs. Day two, I have a new set of data, which is wolf versus cars. So, so the distribution totally changes from what I learned from the previous day. But the goal is to keep the knowledge of the past experience. So this model at day 5 or something should able to not only classify dog versus horses, but it should able to classify cat versus dog also. So usually what happens in like deep networks is they are this very lazy, they used to be very lazy, that if you have a single network and you train a task count of this network, it uses all of this capacity to learn this single task. So it's not that intelligent to like, okay, this is a very simple task, I can only allocate a small part of my memory or capacity to learn this task. It's not going to do that. It's going to use all of its capacity to learn this single task. Then we move to like a new task. So there is no place to learn this new task. So what it can do only is it has to replace, or it has to erase the previous knowledge and has to learn this new task. So that's the main problem we are working with this continual learning. So the goal of the continual learning is to remember what it has learned in the past, but without the access, or without having access to this previous data. So this model at day 5 don't have access to this data, this dogs versus cat data, but it should be able to classify cats versus dog. So that's, I hope you guys understand this problem. So that's a basic idea of continual learning. Um, yeah, so let's move on. So so there is this, like, it's just something like this, like we have an exam and we need to study for like 10 chapters for this exam at day 10. So you study chapter 1 on day 1 and chapter 2 on day 2, and like that. At the end of the day, at the exam day, you need to be able to remember all this information you studied over these 10 days to pass this exam. So that's the exact setting of this continuum. It actually happens with all these babies learning from nothing, and the humans actually do this, right? We start from nothing and we continually learning new things, but we know what we learned in the past, most probably. Like, we still remember like our childhood days and something. So that's the main goal of this continual learning with neural networks, how we can achieve this human level continual learning with neural networks. So there are these couple of techniques or ideas we can use to achieve this with continual learning, sorry, in neural networks. So first one is experience replay. So that's very similar that we usually do that. Say you are studying at at the third day, and you somewhat want to revise your chapter 1 and chapter 2. You use the book and you revise some chapters, so you sort of reinforce what you studied previously, so you keep remembering that you are able to remember some parts you studied previously. So that's usually we do all the time, right? So that's experience replay. And then there is this dynamic memory. So as I told earlier, like we have these neural networks has this issue that they allocate all this capacity to a single task. So there at the end of the task, there is no place left to learn a new task. So what we can simply do is we add more parameters to this network. So at the end, after that, the network was able to, once it's trained on a single task one, it can use the new parameters to learn a new task or the second task. So that's this basic idea of dynamic regularization. Sorry, dynamic memory. And the regularization. The regularization is something I don't really have an intuitive explanation how this happen in humans, but the idea is that you have a small set of like previous, like you keep some sort of like previous knowledge in a small set of buffer and use this previous sample to regularize what you are learning currently. So that means uh, you don't want to raise the previous knowledge by when you are learning the current knowledge. It's bit confusing, but the basic idea is that um, the new knowledge, so we are learning the new knowledge and the past knowledge, right? So we want trying to find some sort of a common ground between this new knowledge and the past knowledge, so that the new knowledge can does not have to raise what is learned in the previously. So that's the basic idea of regularization. But this talk we will mostly focusing on dynamic memory. So okay, so I will talk about this paper, a random path selection network. So this is mostly similar to this dynamic memory of this network architecture. It's a simple network architecture, but it can able to continually learn new tasks as we increase number of tasks along this time axis. Do you have any questions so far? Okay, I guess it's good. Okay. So the random path selection network, it's pretty straightforward architecture. So uh, are you guys familiar with ResNet architecture?
Yes.
Okay, I assume yes. All right. Okay, so think of this. This is the depth of this network, and this is the width of this network. So if you give an image, the image will go through this way, and you will give an output at the end. And these are the every layers of this network. So and so usually what happens is the network image go through layer by layer by layer by, and it will give the output, right? So what will happen here, we have this inside this one layer, we have multiple parallel layers. So each of one of these is a layer, and it has a on off switch. Okay, so that means I can turn this one on. Say I'm turning different switches on at different times. So rest of them will be off. So if I send an image to this network, it will go through the like this. Okay, like here, it will come like this. Okay, this looks like a zigzag path, but if we just unroll this, it will be a straight line, right? At every layer, it will have a single module used, right? Is it clear? Okay, so if we just unroll this network, it will be a single ResNet architecture. There is nothing strange here. It's just a simple ResNet architecture. So for task one, what we can do is very straightforward. We turn off randomly choose a single module in each layer and turn off rest of everything. And at the end, we just need to train this whole single ResNet for the task one. So once we finish task one, we are going for new task, right? So as I said earlier, this if it, this red path is totally allocated for task one. So if I train the same network with a new task, it will totally going to erase this previous information in this task, right? So what we need to do is we need to keep this information. So the simplest way to keep the information in this task is in a neural network is to freeze all the weights. You are not going to train this weight anyway. So all these weights are frozen. So for the second task, that means we are going to learn a different task. So we just randomly choose a different module. It's just a random selection. You just need to choose a random module in each weights. So the information flow will be something like this. It will go like this. Mhm. Like this, like this. Okay, so now we can think of this. If we just look at this part, any single layer, it will be looking something like this. So this is a layer one, this module, and then there is this another module somewhat parallel to this architecture connected to this one. Is this ring a bell? I think it should. So it's a very much similar to a skip connection in a RESTnet, right? So the new task at any level is a skip. It's a residual or like a skip connection for the previous task. So I hope you guys know that the skip connection or the residual learning means that you only need to learn any extra information you need to learn from the previous task. So think of this like this low at the neural networks, the low level information, the low level layers usually learn like low level features, right? That means like blobs or edges or mm, some like low level features of the image. So that's some always most probably common to all the tasks, right? If you want to detect cats versus dogs, the low level features of the cats and the low level features of the dogs are most probably similar. So sorry, so this new path has to only learn a very small amount of information that is different from the cat's data set. And so that's very easy to learn, right? You don't have to learn everything from the beginning. You only need to learn a very small amount of information for this new task. And also what we are doing is we are preserving the knowledge of the past task, because these red modules are frozen. So we are only training this blue blue network. So that's the basic idea of this RPS network. So the selection strategy is very straightforward. You randomly choose a module and it works considerably better than any state-of-the-art networks. Uh, okay, so that's the main architecture story. You guys have any question? Please ask me. It's all good.
Yeah, probably they might have put in the Slido, but we will forward those things at the end.
Okay. Okay, sure. No worries. Yeah, so this is the basic architecture, but there are, like, I'm skipping some technical details, but that's fine. So
Uh, Jatu, I think the at the chat one has asked a question at inference time. How does it know which path to take?
yes, that's a very good question. I'm going to talk about this one. Yeah,
Okay, yeah, that's fine.
that's really good question. Yeah, so, so I will still working on this training path, right? So there is this one training path, and there is this one testing path. Sorry, a second task. Blue one is again a training path, right? So we are training these two different paths, and again there is something I wanted to talk, that at when there is these overlaps, there will be overlaps, right? Because red path, if all the modules in this red network is frozen. So if there is an overlap happens between red and the blue path, they has that modules won't be trained. So that's a basic story of the training. And when we move to testing, yeah, so the input images, we don't know what the task is, right? So that's a really good question. So if you have an image, it can be from the task 1 or task 2. If we know what the task is coming from, then we can choose the path according to it, and we can only use these train modules for that. But we don't know that, so that's a even harder condition to learn this continual learning. So that's the actual setting we are using. So we don't know the task, what's the image is. So what the simplest way we can do is we use all the previously trained modules at the inference time. So at the training time, at maximum, there will be only single equivalent ResNet will be trained. But at the testing time, there will be like maybe 5 of the ResNet in parallel will be working. You can see here, I think this is the inference setting. This picture is a bit confusing. So, okay, so this is a training path. You train this network, and this is these dark green modules are already previously trained. So as we go, there will be lots of modules already trained, right? So it will give us a sort of this grids network architecture. And as we go, like, increase the number of tasks, if we go like after 100 tasks, this the network sort of going to saturate. So what will happen is, at the say at the task t or t plus j, we have, if you, I hope you guys can see, but at the layer one, there are three modules were trained, right? So at the inference time, the image will go through all these previously trained modules, because it will work, because at the even at the training time, we have we have trained this a single path, but this is a skip connection to the previous task, right? So that means this one is going to learn only some additional information to the new task. So that means the previous information is always preserved. So if you send the network image to both of these paths, it will going to sort of have more impact on um, its own path. I hope that's clear. But if you have any question, just write to this website, and we will discuss this in depth later. So at the inference times, so the training is only trained with a single network. That's okay, because we have lots of issues with the GPUs. We cannot train multiple networks in a single GPU. But inference is fine, right? Inference is mostly happen in CPU. So inference time, all these modules will be used to train the network. Cool. Sorry. at the inference time, all these modules will be used to do the classification. Okay, so these are some results. So you can see, uh, hope you guys familiar with the fine tuning. So fine tuning will be like, okay, let's forget about fine tuning, but just fixed representation. That means fine tuning. This is the like the baseline curve. That means if you just keep training a single network with the new task only, it will totally forget the previous one, right? At the end of the time, it will only remember its past task, the final task. So that means it has accuracy like if you're training with 100 classes. And okay, I think I need to talk about how we do this evaluation. So the usual setting of this evaluation is like we take a CIFA 100 data set with 100 classes and divide it into each task with 10 classes. So task 1 has 10 classes, task 2 has another 10 classes. So we train each task with 10 classes, and at testing time, at the end of the testing, we need to test with all the 100 classes. So if the network has only remember its final task, it only remember 10 classes, it forget all the 90 classes information or the knowledge it learned from this all the previous tasks. Its accuracy is close to 10 percentage, right? So most of these methods are very close to that one. So there are some couple of baselines called ICAL and EWC. So different techniques like as the replay method or the regularization method. But if you think this, the yellow line, that is the RPS network architecture, that's considerably better than this previous state of the art methods. But if you, I hope you guys can see there is this purple dot. So that's the oracle case. That means that is the best accuracy we can get if you train a single network with all the 100 classes. Like that's the best. That's the, if the network hasn't forgot any information, it should be able to come closer to this oracle case. So the goal of this continual learning is to push this curve toward that purple dot. Okay. So that's the basic idea of continual learning and what happens in continual learning. All right, so let's move to few shot learning. So the few shot learning is again, it's a different sort of setting. So I think you guys understand that continual learning is about all about like remembering the past, right? At the end of the training, it should be able to remember what it has learned previously. So I think the title was kind of deceptive, but that's the main goal. So the continual learning will try to remember what is learned previously. So that's the main goal of the continual learning. But the few shot learning, here we don't have enough samples to train a network. So this is like one classical example that we have this sort of a support set and queries image, but we have only one. Look at, we can see that we have only one image for bird, right? So we need to able, this network should able to use this very small amount of information and able to classify this as similar to a bird or like, yeah, bird. So how we can do this? So there are like lots of ways to do this, but a simplest way, or I would say even the best, the state of that methods, you simply use, say like you have this very huge amount of ImageNet data, and learn a pre-trained model. Okay, so if we just learn this huge amount of data with labeled data or unlabeled and learn a better pre-trained model, once we have this model, if this model is equivalent to this model, and we can send this image and get an embedding for each image, right? And ideally what will happen is, even if this, there is no birds or cats in this imaginary data set, it, this embedding will be most probably close to each other. So a simple nearest neighbor classification is sufficient to identify, able to, in a nearest neighbor, these embedding and this embedding will be very much close to each other. So that's a very basic simple setting. So the main goal is to, we have this very huge amount of data, we have data. So the idea is to use this data and to learn a meaningful representation. That representation should not overfit to this data. because these labels or there is these labels or these sort of images were never seen in this data. So this is sort of like a new data set. This network hasn't seen any image or like classes in this new data set. So it's going to like it should the embedding this network learn from this data should be good enough that it should be able to classify an unseen classes. So that's like sort of the basic goal of this future learning. So that's what I was trying to say, that we should be able to learn a very good meaningful representation from and that representation should be good enough to predict future images like that has been never seen. It should be able to do good in these future upcoming images. So that's sort of the main goal of the future learning. So hope that's clear, but if you have questions, like write it to the website. Okay, so we'll discuss one more paper about self-supervised future learning and how we can learn a good embedding uh, for future learning. All right. So, so this is called self-supervised knowledge distillation. So, as we previously discussed, like in the previous slide, that the goal of this future learning, at least in this setting, is to learn a very good embedding that can be good enough for future data, right? So how we can, so the question comes narrows down to how we can learn good embedding. So to learn a good embedding, there are like multiple techniques. So one of them is called self-supervision. I think hope you guys remember, like we discussed like different techniques of learning. So one of these, like if you don't have any labels, one of the great ideas to use is to use the self-supervised knowledge. So what is the self-supervision? So say we have an image, right? And okay, in this case, let's assume we don't know the label of the image. There is no information provided about this image. So how we can learn from this like totally unlabeled data? So apparently what you can do is you can simply, this is one of the simplest idea, but it's works pretty much well. Simply rotate this image and maybe like this and this. Okay, so we have like 4 different rotation of this image. This is like 0 degrees, 90 degrees, 180, and how much, 270 or whatever. Yeah, so you can just simply rotate, and this rotation is very easy, right? You can just do it in like CPUs and like and you are the person is doing the rotation, so you know the angle of this image, right? So it's very simple. So the goal is, then we simply ask the network to predict the angle of rotation in this image. So that is called self-supervision. That means we are the one supervising this network. There is no extra data. This all the supervision signal is coming from the single image. So and actually this is a very interesting idea and it works pretty much well in most of the setting. If you have no data, this is a very good idea. So okay, so okay, where were we? Okay, so this paper is trying to do this future learning with self-supervised knowledge. So the goal is not the goal, but the task. We have this thing. You can see these images, but these images are normal images without any rotation. But these images are like rotated by 90 degrees. This one like 190 degrees and 270 degrees. The same images, but each of the images are rotated. So at training time, we just send all these images together. First part, we just do the classification because in the training data set, we have the labels of the images. So that's first part, that's fine. The second stage, we use is self-supervised loss. The self-supervised loss is simple cross-entropy loss. You have four neurons. Each one has like labels, whether it's first one will be like 0, 1, 0, 0. That means it's rotated by 90 degrees. It's a pretty simple idea. And uh, yeah, so we have these two classification layers and we just train this network with self-supervised loss. And apparently the embeddings learned from this self-supervised with additional self-supervised loss are much better to because it has seen sort of like very huge variety of this data, right? Because it's not going to overfit to this one sort of biased data which always looks forward or looks without any rotation. So these embeddings are okay. So these embeddings are very good at doing this few shot classification. That means these embeddings are more towards able to generalize to a sort of like a unknown distribution. And we have this paper has actually two set of learning stages. I will explain more about this later, but the second, this first stage one is pretty simple. You take the image, you rotate this image, learn the classification plus self-supervision. That's done. And in the next generation, what will happen is that we take this network and keep it as a frozen weights. It's sort of a like student-teacher learning. And we just take two clones of these networks and frost one weights and train the second network. What we are going to try to do at the second stage is bring the embeddings of 90 degree and 0 degree, because of this sequential classification layers, embedding for a same image. Usually what happen in a neural network, if you train, if it is image one, its embedding is same even if you rotate or change whatever, right? It's the same embedding. But in this setting, it has a different embeddings, right? For each rotated version of the image, there will be two different embeddings in this like classification manifold, I1, IT or something. So each of the embeddings are different. So what will happen actually is that because there is a different embedding for each image and each rotated version of the image, it will sort of explore this loss surface better than any other networks, because it has points, lots of points compared to this simple learning, because we have very few short examples to train. So we need to explore the surface, loss surface much better than this normal training. Yeah, it's similar to like a very, if we as if we have like large number of data. So what we can do, how we are going to do that is we create sort of these fake or augmented samples which were rotated version of this image. They can be like at different positions, so it will create a very well explored surface space. At this, that's happened. Okay, so this is for image one. For single image, there will be like 4 different embedding spaces. At the stage 2, the idea is slightly different, that we just need to bring all these embedding closer together while keeping this embedding space as it is. So that means for this image is well explored, as well as it going to improve its classification accuracy, because there is a single embedding for each image, but that embedding has been explored this loss surface much better. So that's a basic idea, but if you have any question, please feel free to ask. um, so this is like the same idea, but I talk about again. So this one is a this one, okay, this one is the original image without any rotation, but because of this sequential connection, we will have like different version of this image for the different rotated versions. So because of that, we can explore this class. This is for say a single class. We can explore this surface much better than any other classification methods. But at the second stage, we are going to use this knowledge distillation to sort of anchor these points. That means we are not going to change this classification manifold at any change, because we need a very wide classification manifold to have good we need a very wide manifold to have a better classification accuracy. The better generalization will come if we have a wide manifold of classification manifold. So we want to keep the manifold as it is, but to improve the accuracy, what we need to do is to bring all this embedding closer to together. So there will be most probably there will be a single embedding for all the rotated version of the image at the end, as in any case. But these embeddings has been explored this loss manifold much better than any other learning method. So that's a basic idea. So because of that, we have achieved the generalization because of this very wide manifold. At the same time, we have better classification accuracy because we are bringing everything closer together. So that's the basic idea of this paper. But yeah, all right. So these are some results that this is a very simple method. So these methods are like very complicated methods with like second order optimization and so on. But just a simple pre-training works actually much better than most of these state-of-the-art methods. All right. So that's the whole story of this future learning. So I think you guys now familiar with this idea of continual learning and the future learning. All right. So let's move to this meta learning. I want everyone to really carefully look into this picture. And can someone please tell me what's happening in this picture? I really want to know the answer here. Anyone? Come on. Someone can tell the answer. Okay, I think someone put a. Is there anything on the chat? Okay. And so, yeah, I hope you guys understand this.
Yeah, we
But
received only one
this,
answer. Yeah, one is they are doing a painting. Yeah,
what's the answer, sir?
um, they are doing a painting. So that's the answer.
Okay, yeah, that's a good answer. Yeah, it's correct almost, I guess. Yeah. So this is a painting of a painting, right? So this one is not a photograph. It's just someone has drawn this painting, thinking that there is a painting happening inside this painting, right? So that's called this meta painting. That means it's a painting of a painting. So this is called Les Plasmanis. It's from the Diago. So this he is the painter actually draw this painting called Diago, and this is from like he's a Spanish painter, and like this is from Golden Age of Spain. But the idea is that this picture has meta information about the painting, right? There is a painting happening inside this painting, so that's a basic idea. So the meta learning is almost the same similar idea. That means that it's about learning to learn. It's same as it's a painting about a painting. It's a meta learning means it's a learning about learning. So think about like you go to some seminars where they will teach how you should study for your exams, how you should like write answers to get good grades, something like that. So it's about learning how to learn for the exam. All right. So that's the basic idea of this meta learning. Actually there is like lots of ways to do like learn good meta learning, but one of these popular method is called MAML. So that means model agnostic meta learning. So um, I think I will skip these more technical related details, but on high level, what will happen in this, sorry. Okay. So in this meta learning is, say you have a model parameter theta, and the meta learning is about, you want to learn how to learn, right? So say, oops, sorry. Okay, what happened? Okay. Okay, so you have this set of a parameter theta, neural network weights, and you are learning as a task one. These are gradient steps. So that's what usually happens, right? You have this task one, theta one. So say this one is cats versus dogs. So this is a single task. And then use the same parameters as initialization and move to a new task, learn a different task, and maybe theta 2, and this is maybe cars versus plane. So each of these tasks is about learning a single task, right? Each of these paths, you can think of it as a learning a single task. So the meta learning is about how we should able to, how, how we can find a better way to learn a different task. So that's the basic idea of this meta learning. And the MAML algorithm is actually how we can move this parameter theta in a direction such that if it comes here, say theta prime or something, you can easily go to these two tasks quickly, right? Because it's closer to these optimal parameters. So that's the basic idea of this meta learning. So you want to find a meta parameter theta such that it can quickly adapt to this new information. So that's the main goal of this meta learning. But if you have any question, please feel free to ask me. So I think I will move for this next slide. So as the title of this talk is that we want to use this meta learning. That means meta learning is actually a very good way to achieve generalization. So we want to use this meta learning to improve or improve the performance of incremental learning as well as few shot learning. So that's the main goal. So the next two papers we're going to discuss is like we have already discussed two papers on like continual learning and future learning without any meta learning mumbo jumbo, right? So it's just simple um, continual learning with like normal classical architecture as well as future learning with self-supervision but without any meta learning. So the next two papers we're going to discuss is continual learning plus meta learning, how this meta learning going to improve the performance of continual learning as well as um, future learning with meta learning. So how we can use this future learning, sorry, meta learning to improve the performance of future learning. So that's the whole idea of this talk. So the first one is ITML. It's abbreviated for ITML, incremental task agnostic meta learning. So the idea is that I think you guys now familiar with the concept of incremental learning. It's the same as continual learning. So we have sorry, we have a set of different tasks, right? So the task one, task two, task three, each of them will come at a different point in time and incrementally they are going to come. So if we start with a randomly initialized neural network weights and train task one only, the network is going to give like use it all this capacity only for task one. So that's fine. When we go to task two, if we don't use any sort of these meta learning tricks, just simply train with task two, what will happen is these weights, everything is going to be dedicated for only for task two. There is no information. Uh, the previous information is not going to preserve. It's going to erase all this previous knowledge about yellow task and totally going to rewrite the red task. So that's fine. That's bad. We don't want to do that. So that's where this meta learning going to come. I will explain more in details, but with meta updates, just if we don't do this classical gradient descent or like normal SGD updates, but if we use the meta update, we can preserve previous information of yellow task as well as we can update or add new task to this network. But note that here we are only dealing with a single network, right? So this is just a single simple rest net. In previous we have to have this multiple, maybe like eight or equivalent to sort of 8 different neural networks to have incrementally add new knowledge. Here we have a single network but able to add more knowledge to this network with the meta update. So that's one of the interesting point. And for task three, we can do this meta update, and this network at the end of the task three have all the information necessary for task one, task two, and task three. But this network is actually called a meta network. That means it has the information about all these previous tasks, but it's like it has the information, but it's not going to give you this information directly. That means this network is sort of in a common ground. So this is theta 1, theta 2, and theta 3. Think of this is a very simplified explanation, but this meta network, it falls somewhere in the between of all these three optimal networks. But to have a good classification on whatever the task we are going to work with task 2, that means we need to move this network towards task 2. So that's called the adaptation process. So usually the meta learning has two loops. That means inner loop and the outer loop. The inner loop is usually works with adaptation. That means move this meta parameter towards the task specific parameters. So these are task specific parameters. These are task agnostic or meta parameters. So when at the inference time, what we're going to do is, if we just send this sample from the red task, so the task 2, this network is not going to give us any good information or any good classification label for this task, because it's a meta network, right? It doesn't have good information about task specific weights. So, but actually, what it can give us is, it has sufficient knowledge about what the task it might be. So, we take one image from this task 2 and send it to the network. It can just tell us, it can only tell us this sample is from task 2. That's only thing we can get from this meta network. But within some like um, this network has all this information about task 2, but it's sort of under the rug, right? We cannot access this information. To access this information, now we know this image is coming from task 2, right? So we keep a set of memory, so a small buffer which has a subset of information of each task. We have a small, like 10 examples from task 1, 10 examples from task 2, a small image. And now we know it's from task 2. We take the example from the buffer or the memory and do this adaptation, just a simple gradient steps. And because of that, this model is going to become a task specific model for task 2, right? And this model can able to do very good classification for any of these tasks. So this model can give us a very good classification for task 2 only. But if we send the image from task 3, it's going to fail. So what we had to do is, we had to send it again and do the adaptation again. So every time we send an image, we need to do the gradient step adaptation. All right. So that's the basic idea of this incremental learning plus meta learning. So how we are running out of time? Are we running out of time?
No, actually, if you want, yeah, you can take about 10 minutes more.
Okay. Okay. So I'm kind of going to rush through this, but yeah. Okay. So the main idea of this goal is to learn, right? So use this meta learning approach, learning to learn, to achieve this generalization, because the main goal of this deep learning is to achieve generalization. But how we going to do is the question, right? So even continual learning, online learning, future learning, all of them requires a good model with a generalization. So if we can achieve this generalization, which is, the meta learning is especially very good at achieving generalization. So that's the main idea of why we need to combine this meta learning with continual learning. I'll skip these parts. Okay, so I'll just go through this one. Oops. Um, so this is how we going to do this training for item. So think of, we have a small data set. We want to learn a new task, which is say green task, and we have a memory, like we have a lots of sample for the new task, but in the memory there's a like very small, maybe 10% or 1% of the previous task are stored, because eh, theoretically in continual learning we cannot have access to any previous task. Got it? So, but usually what people do is, we have like a very small amount of task memory, which has like 10% or like 1% of this previous data, because it's something similar to experience replay, right? You can access this memory at any time and sort of restudy or reinforce this previous knowledge. Yeah, so that's okay. So we can sample from this new data. We'll get a mini batch. This mini batch has the set of, it has all the tasks from the previous memory, this memory, as well as the new memory. What we can do is, we're going to group this mini batch into a set of micro batches. That means a single micro batch is belongs to only a single task. Okay, so we learn a model. These are sort of task specific weights. We learn this model to create these task specific weights. So it's something like we have theta and theta 1, theta 2, theta 3. So the simplest way, because the ITML is somewhat similar to a first order approximation to MAML. It's actually a first order approximation to the MAML algorithm. The simplest way to find a closest weight through the simplest way to find a closest weight between all these these weights is to take the average, right? So the final weight, we just move theta to somewhere. We 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 need to move this theta to somewhere close to this theta 1 and theta 2, theta 3, that we can simply do in a first order approximation. Just take the average of these all these weight. So that's what happening here. We just take average of all these weights, and that is going to be our meta parameter. So the meta parameter is simply speaking, it has information about all these different tasks, right? So that's the goal of this meta parameter. So now if we just take average, it has the information about all these previously learned tasks, all these tasks, it's captured here. And of course, this is not really important. In outer loop, we just do this exponential average, moving average to keep a smooth transition between weights. So that's a basic idea of training. I'll skip this part. This is actually interesting note. So usually what happens is that in a neural network, we can sort of dissect it into two set of parameters. So this backbone, these convolutional filters, we can keep it as a meta parameter. And this final classification layer, say pi, we can keep it as a task specific parameter. So what happens is that the meta parameters, which has the general knowledge about all the tasks. So these are the task manifold of task 1. This is a task manifold of task 2. So the meta parameter is sort of like follow the zigzag path and end up somewhere in the middle of this task classification weights, because it is not a biased parameter. It's a general parameter, right? So it has to be somewhere in this middle between this optimal manifold. But these task specific parameters or these classification parameters usually stay close to this optimal manifold. So that will be somewhere here. So that's the basic idea of this ITML. We do this meta update only for the meta parameters. That means we do this meta update, this averaging thing, only for these convolutional filters or this backbone of this network, and keep this final layer classification as task specific as it is. So at the end of the day, this is the main reason that the network is still able to give us a good task score. That means the network can still able to identify what the task is. That's the main problem, right? If all these parameters are meta parameters, that is totally useless. That means we cannot get any information from these meta parameters. So we need some part of this network to have this task specific information. It can be wrong, that's fine, because the class accuracies will be wrong, but on average it can able to at least able to identify what the task is. So that's the main idea of this paper. I'll skip this one. This is again the same thing. So at the inference time, we don't know what the task is. We send it to the network. We can have this sort of like classification scores. We just pull this one into a single value. That means some all these values, or take the average of a single task. So we have this task scores. We call this as a task scores, and based on this we can at least able to identify this data is belong to a purple task. Okay, so we go back to the memory, and in the memory there is a purple task. We use the samples from the purple task and do this gradient update. So this new model is task specific models. This gradient updates on this meta parameters. So the total network became task specific for this purple task, and now it can able to give us a very good classification score on this new task. So that's how the inference happens. I'll skip this one. Okay, so this is interesting. That means you can see this yellow line. So this is happen. These are the plot from this previous RPS network. So that the results we got from the RPS network. But with this meta learning, we can really push this limit very close to mm, uh, the oracle case. That means that is the best we can achieve if we have trained with all tasks. So that's a very interesting thing, that with meta learning we can really improve this continual learning to a next level or high level. Okay, I think okay. So we some tables, boring tables. Think think I'm really running out of time, but I will just take 2 or 3 minutes to finish this one. So then there is this paper, like, okay, I was talking about meta learning plus continual learning till now, and now we will finish with meta learning plus few short learning. So I already discussed about this MAML paper. So it's a very interesting paper. It has this adaptation, and after the adaptation, use the second order gradients to move this meta parameter to a very good initialization point between theta, all these thetas. So how this is actually, if you think of this MAML, okay, if you think of this single path as a optimization graph, it will look like this. You take this parameter and do a gradient update. So theta j plus 1 equal to theta j minus gradient of theta j on loss theta, right? So this is the skip connection you add. This is the negative of the gradient. So this is the usual, like, normal gradient steps, right? So this is the inner loop function of MAML. I will skip this part, but what the Pamela does is, if you think of this as like a normal ResNet problem, this has very much similarity to ResNet, right? It has the skip connection equivalent to the ResNet. It has a sort of this convolutional features equivalent to ResNet. So that's the basic idea of this Pamela paper. That means in an optimization graph, we can skip the gradients, not the features, but the gradients. Then the gradients from the low level will sort of skip to the high level information. So that's the basic idea of this one, but I'm really running out of time. Okay, so that's the idea here. Rather, this is will be a MAML optimization path, but in a Pamela, what will happen is the, okay, I think I will just draw this theta one. So sorry, theta. So this is our parameter. We use these gradient steps to optimize to theta 1 for task 1. But, to optimize this meta gradient, what will happen is the gradient has to back propagate through this whole optimization process, right? So what will happen is, like ResNet, why we created ResNet, because we don't want to vanish these gradients going through a long optimization path, right? So what we can do is we can skip this gradient to a high level. So that's the basic idea. If we can just skip this second order gradients to a high level, so the information about this low level information can be preserved. So that's a basic idea of this Pamela. There is interesting thing, but I will skip it for now. But if we use this sort of idea, it can able to perform slightly better than this state of the art methods. It can be better than the MAML approaches. Okay, so I think I'm ready to conclude. So we have talked about continual learning, meta learning, and visual learning, and we already discussed about some papers. So if we combine meta learning with future learning, we can sort of learn some better representation, as well as with continual learning plus meta learning, we able to improve the performance of continual learning when we join with meta learning. So the title of the paper suggests that we are looking for the goal of this, the overall big picture is that, can we find a better algorithm which able to sort of combine these three dots and able to learn some better, it should be able to do better at continual learning. That means it should be able to remember the past of the information. It should be able to contain the previous information, as well as its embedding or its features should be able to do good classification at the future. So that's the overall big picture we are trying to solve, but it's still ongoing research, and it's a very hot topic. But if you are interested, like, give it, read about it, and it will be helpful. All right, I just wanted to thank my collaborators on these projects, Professor Salman Khan, Munawahar, and Fahad. And I think thank you. And if you have any question you haven't asked, you can just feel free to write me an email. Cool.
Thank you very
Thank you.
much, Jatu, for actually this is very interesting topic on the recent advances on machine learning, yeah, basically the continual, few short and the meta learning, and how you are going to combine each of the domains to
Yeah,
reach to that ultimate goal oracle.
yeah, I'm
And
really
yeah,
interested.
yeah, it's really nice to see. And so actually, we can move into the questions in the slide.
Yes.
Oh, but yeah, before that, I think I have received two things in the chat. One is from your colleague, I think we know. So he has mentioned
Okay.
that, yeah, thank you very much for the very interesting talk. Yeah, it's a,
Okay.
yeah. So
Thanks for
yeah,
coming
so
in.
appreciation. And so there is actually discussion came in the middle, but I did not interrupt it. So the uh, one participant asked, can anyone from, yeah, can any form of task be combined into one model? I think it's related to that the meta learning and Pamela work. It comes, yeah. Can any form of task be combined into one model? Like, can a regression and classification be combined in the same model? So
Mm, dear, uh, can you please repeat this question?
yeah, so basically the question is, can any form of task be combined into one model? And so as an explanation, it is mentioned that can a regression and classification be combined in the same model?
I see. I see. Okay, okay. I think I understood the problem. So, question. So he's asking like the definition of a task, right? Mostly the is come in the problem of definition of the task. So the answer would be yes, but in most of these examples or most of these papers, we really don't have this sort of very large distinction between tasks. So the task in most of these paper we are dealing with is a classification, but the task is like you need to classify cats versus dogs and then cars versus planes. So that's like the same domain of images. Because if you want to do the regression, I mean that's possible, totally possible, and the answer is definitely yes. But in most of these works, we are not really interested in that sort of domain because um, it's one answer would be, I might be wrong, but the one answer would be we may not be really interested in having these totally different tasks, right? Because think of it as like you have a street camera and like you want to detect cars or something. So the continual learning aspect of this changing task is that at the daytime the images are going to be like normally bright images and so on. At the nighttime images are going to be more like dark images. So the distribution is changing, the task is changing. That means the task at the daytime is you need to able to classify daytime images. At the end, at the night you need to able to classify the night images. But the distinction is very minute, right? It's very small. Those are the problems we are really interested in there, because there is no I haven't really faced that at the night time we will be able to, we need to do totally different tasks. Like at the daytime we are going to do the tracking, at the night time we are going to do classification. So that sort of distinction is not really happening here, but the answer is definitely yes, we can do that. I
Okay,
hope that's
so
answered your question.
yeah, so actually, yeah, Bhavan actually is a moderator for the question and answer. So he has put the first question actually in the chat. In continual learning, in some case, if we want to adapt our model to a new set of data that comes from feature, then can we do this using meta learning idea? So if it is not clear, you may read the chat actually. Yatu, so basically he asks, in continual learning, in some case, if we want to adapt our model to a new set of data that are, yeah, that are coming from feature, then can we do this using meta learning idea?
Uh, if the data is, so the main problem with this continual learning is the distribution is changing, right? At the start you have a totally different distribution. At the next task is going to be slightly different distribution from the previous distribution. If it's the same distribution, then there is no problem. So if your data is totally new data, it has like, I didn't understand the part. It's coming from the features. How does the data comes from the feature? Then we can use this meta learning idea. Hmm.
Yeah, probably
So
if the person who, yeah, the participant who asked the question is in the audience is still, so the he or she may unmute and have some explanation.
yeah, yes. Okay, so like
Yeah,
it
so
is
then
not
actually,
about.
yeah, until it comes, yeah, let's go to the second question. So the how
Yeah,
do
I
you
just need to
visualize
like
and
sort of
study the
wrap this
embedding created
presentation
for
maybe.
each images? Yeah.
So the answer is that I didn't understand the feature part, but if you have a model pre-trained on some previous data and you want to use the network to with the new data, you can simply, if the goal is not to keep the both information of the model as well as the new data, you can just do the fine tuning of transfer learning. But if you need to keep information about this model inside this model as well as this new data, then you can definitely use continuous learning and it will definitely work. And meta learning, the problem with this meta learning is that it has to have multiple tasks so that it can able to generalize to any new task. So if you have, if you only have a new single task, then it's very hard to do meta learning on this task. Actually you cannot. So the only way you can learn a model for a meta learning is that you need to have multiple tasks. So if you have only single task and a model, you can directly go with knowledge distillation to preserve the previous information as well as some continual learning aspects of it. Yeah. Okay, sir.
Yeah, so the second question is how do you visualize and study the embedding created for each images? Each image, yeah, basically.
So, that's a good question. So that's interesting. I think I might able to show some figures if it's okay. Uh, where is it?
Okay, so this is a confidential review copy, right? So we all see anyway, that's fine.
How to compile? Okay, this one. Okay, it's taking a long time. So the idea is like you can actually visualize all these features created by the network. So usually what we have is like a single neural network, right? And the neural network is going to give us like logits, or at the end you will get sort of like, if you the data is like 100 classes, you will have 100 values for this one, right? So the visualization space is usually 2D, right? Two-dimensional space. So what we usually do is we can simply do a PCR to reduce this embedding space to a two-dimensional space, and we can just plot XY coordinates on top of that. This. So that's the basic area. You take this embedding from all these image, you send the images, you get this embedding or like logits. Embeddings means that before the softmax layer, or take the logits, do the PCR on all these weights, all these embeddings, you will get like only two-dimensional vector, and just plot this vector with these values. So it will create a nice clustered plots of these values. So all the images from the same class will be clustered together.
So is it equivalent to the TSNE diagram? So
Yes, yes, yeah. Yeah, TSNE would be much better, but it has its own pros and cons. It will be slightly slow, as well as most of the time it does not preserve the structure of the data. That means
okay. Mm.
with different seeding or different starting points, it will create different sort of plots every time.
Mm, 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 mm.
But it doesn't, that's the main issue. It does not preserve the structure of the data.
Okay, yeah. So the third question is the actually is transfer learning also kind of similar to few shot learning?
Transfer. Yes. Uh, its answer is maybe yes and no, because uh, transfer learning can be thought of as a part of a few-shot learning. Okay, so maybe I will
Yeah, this is
quickly
a
talk about.
visualization, right? Yeah.
Yeah, so this is the visualization. Took a while to get this one. So if we just do this again, if I remember correctly, this one is like without any self-supervision loss. But these plots were created if we have a self-supervision loss. That means if you have a self-supervision loss, you can able to like cluster them much better. Those will be much
Mm.
like you can clearly see a better boundary between two classes, right? So that's a basic idea. But you can visually simply do this one with TSNE or PCR. Okay, so the
TSNE,
transfer
other one
learning.
is PCA.
Sorry, sir.
Other one
Uh,
is it?
sorry. PCA. I was thinking about PCR all the day.
Yeah, 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 that's right. So that is
Yeah.
principal component analysis, right?
Yeah, PCA. Yes.
Okay.
Not PCR. That's the Corona days.
Okay, yeah.
Uh, yeah. The transfer learning is actually somewhat okay. The idea of the transfer learning is you are going to change this neural network weights to a new data, right? So, but the MAML algorithm is actually, we can think of it as a transfer learning. It's actually retrain a network and do this fine tuning or adaptation on the network. So that's actually what the transfer learning does. But the MAML does it in a better way. That means that usually if you do the transfer learning, you train, pre-training part is fine, right? You learn a network with large amount of data, that's fine. But when you do the fine tuning, what will happen is that you have a very small amount of data for visual learning. But if you do the fine tuning, huge network, small data, it's going to overfit or it's going to underfit, whatever. So that's not going to work. So that's where the MAML comes. It has a clever way to move these meta parameters very close to these task specific parameters. So that means a single gradient step or one or two gradient step with a few data is sufficient enough to move this network to this task specific parameters. But the transfer learning has to move a very long from far from this network. So that's a main problem. I think I can just quickly draw. You have this parameter. So the transfer learning has to move this parameter to this theta one. But it's very hard to do this because the gradients are like, we have a small data, so the gradient's going to be very noisy. So the gradient will converge it somewhere else. But the MAML does is, MAML move during this meta training, the MAML move these theta parameters very close to these task specific parameters, right? So because of that, one of the small gradient step is sufficient to do this fine tune adaptation. So transfer learning is somewhat similar to the fine tuning feature learning, but it's not really helpful. We cannot, the process is same, but the results are not the same. I hope you understand that.
Okay, yeah. So the first question is, what are the recent advances in few shot learning literature in terms of self-supervised representation, yeah, self-supervised or representation learning, apart from SKD paper by yourself? Okay, so
Okay. Okay, that's a tricky question. Yeah. Okay. So yeah, there is definitely new papers coming, but one of my favorite is that EMD paper. EMD. I might able to find it. Maybe EMD VPR 2020. Okay, I think.
is it DPMD or no? Oh,
Yes. Where did you find? Okay, okay, this one, yeah.
The top
So
one.
this is like interesting paper. Yeah, it has like very good results also. Uh, just give a read, but the main idea is that, okay, I think I can show some figures here. Yeah. So the main idea is to not use this whole information. It's again somewhat similar to this self-supervised learning, but you break these images into lots of patches. That's why you can get more. Because of that, you can get more data, right? So that's a basic idea, and use this to match this earth mover distance. That means legs should be matched to legs, face should be matched to face. So that usually very, if we have very small amount of data, it's very hard to match the whole image to this one. But if we break them into patches, and this has much more similarity than these whole two images, right? So that's a basic idea. This is an interesting paper. They have very good results. And for future learning, what else we have? I think we were discussing about some other papers also, but there's this paper also. There's, okay, free lunch for future learning. So this is an interesting paper that the main idea is that if in future learning we will have these two set of data, right? The support data. We have some data, but it has very small amount of data. So we first try to calculate this statistic. That means the mean and variance and some high order statistics to this uh, um, support set. That means whatever the data we have, we try to calculate this support set, the statistic of this data. And when we have this query image, that when what the image we want to classify, we send it to the network, we find its mean and variance and something, sorry, and adapt to this new image to the same statistic as the support set. So that's the basic idea. That means it has to come from the same distribution, right? So, but this works also pretty much better than like the current state of the methods. Yeah.
Okay, so
That's
the
all.
fifth question is the what are the research areas in computer vision we can focus as undergraduates to contribute to the research community? I think that's a you can take 1 or 2 minutes and give your experience and because
Yeah.
there are a lot of undergraduate students who would like to do some research contribution and
Yeah. Of course, like, don't think like any of these areas are really, really hard areas, but you can actually contribute to any of these areas. So that would be my opinion. I was personally like this area, but if whatever the area you like, you can definitely contribute. There is no issues. It's not that really hard. You can definitely do it. But sort of like biased opinion of in my perspective would be uh, these recent times, like, so like if you really so this is sort of like a trick. If you really want to get like papers published and to do like fast contribution, so like 2010s to 2000, like 2010 to 2019, this century was like fully dedicated for convolution networks, right? All of this classification, detection, everything is done by CNN. But I think 2020 and this next decade is going to be mostly dedicated for transformers. So transformers are early started with NLP, natural language processing problems, but it's sort of slightly taking over the computer vision and all this. It beats ResNet. It can be now used to do detection or tracking. It can sort of do all the computer vision tasks with transformers. So what currently people are trying to do is just to replace the CNN in the detection pipeline with the transformers. But transformers has much more potential than a simple, um, rather than a simple single CNN or classification network. So you can think of like very creative, innovative ways to create a different architectures for transformer itself, or you can use these transformers with like different any sort of computer vision problems, like even continual learning or like future learning. So the transformers has like very good, how can I say? Transformers has this potential that they actually do this set operation. That means given an input set of inputs, it's actually able to communicate between all these pairs of input, because like if you have a CNN network, it will only do this kernel, it's moving this kernel, right? So it's by 3 by 3 kernel. So because of the layer, it can talk with all these parts of the network, but that's sort of like handcrafted. But transformers can actually talk with all part of the network or image between its architecture. So that's a very good part of the transformers, and it's doing pretty good. So I think that would be like a very good direction to get like very good publication with like contribution to the community, because I believe this decade is most probably going to be dedicated to transformers. So that's the one thing. And yeah, like these like self-supervision is like one of the interesting topics, and it has been shown pretty tremendous like outputs, like performance. It can be used with like most like, even if you're working with signal processing, you can definitely use self-supervision. Like it doesn't have to be image, right? So it can be used for any sort of data. And personally, I like continual learning. That's really like, so the like a very long-term goal of like machine learning is to able to mimic human learning, right? So if you think of that way, like we started from nothing, we continually learning new information. So continual learning is very much important for this sort of like long-term goal. So that's the one really interesting topic. And and also like think crazy, like you can think of like combining all these learning theory, like continual learning plus meta learning, or continually learning future learnings. All of these different aspects can be linked together. So that's the interesting topic. You can think like semi-supervised continual future learning, something like that. And that can create like neural architectures for something that could be really interesting. Yeah.
And in the meantime, so the one participant, actually, Mohammed Afam, I think he has sent a link actually for the Transformers in Vision, yeah, archive paper. And yeah, thank you, Mohammed, for yeah that one. And
Yeah.
so the I have actually few questions. So I am basically working on the this signal processing, not in the machine learning. Yeah, I'm collaborating with some people with who knows machine learning, one of you. So the so actually I have seen the I'm these days studying about the graph signal processing. So basically the graph neural networks. So and also the other idea is that the GANs, generative adversarial network. So the what would be the future of these things in this decade, and
So
GANs
as I
and the
said earlier, like, so CNNs, graph neural networks can be CNN is something like a subset of a graph neural network,
oh
because
yeah,
CNN is sort of like hand-wired graphs, right? But
yes, yes, yeah,
graph neural networks has this like sort of general graph, so it's has this much better circle, right? So,
hmm.
but the transformers is actually even much better.
Okay,
It even so like any sort of CNN or GCNN can be classified as a subset of a transformer operation.
transformers. Mm-hmm.
So the transformer is like it can be connected to all the nodes in the graph, and it has multiple layers.
Okay,
So, but it's and also it's very good at learning this information. It has
mm.
this self attention.
Self attention, yeah.
Yeah. Uh, so there is this paper space time graph. So let's create this graph, and like if you have a video, it creates a graph for each of the time step and space. So it create a graph and it can do this video classification. So but now people have used transformers. It has much better results than the graph neural
Mm,
networks.
Okay, okay,
So
okay. Yeah, thank you for
okay,
that.
yes.
And also, see, so basically, I'm working on the light fields and recently some of the biomedical image, not image actually, EEG and ECG signal processing. And yeah, we had one meeting with you as well. So
Yeah.
basically, they are the one of the major issue is the limited data as usual. So and so in applications, right? How could we incorporate this few shot learning and meta learning into this kind of application? Yeah, for example, heart disease classification, or in the light fields, it is depth estimation, or the like saliency detection and super resolution. With yeah, how could we incorporate? Yeah, because you are working in the theoretical area of this.
Yeah,
Yeah,
yeah.
new algorithms. So I'm more in the application level. So the how we can incorporate those.
Just a quick thought in my mind is that if you want to do this classification of like like ECG signals, but you have like say 15 different disease and you have
Mm,
like 10 only 10 samples for each diseases.
mm,
So one way we can use this with like future learning or something, or like training is um, so there is this one way that we don't have any unlabeled data. We have like lots of unlabeled data. We have labeled like sickness, but we don't know what the disease is. Maybe that would be much cheaper to get. Then we can sort of like learn this sort of auto encoder that
mm,
given an image, sorry, signal, it learn a representation, and with the deconvolution, it has to give output the same image. So it's a very simple L1 loss, or like the input and output are the same. The network has to learn this mapping. So once we train this with unlabeled data, we can take only these embeddings and use these embeddings to do the few shot learning. So that's the
mm,
one area. But if you don't have this unlabeled data, but you have say now we have 15 different tasks, right? So we can do this meta learning to learn some like meta representation for the whole task. So we have 15 tasks. So randomly choose 5 tasks at a time and learn a meta representation for 5 tasks. Do the meta update. Randomly choose another 5 tasks. Optimize for different 5 paths,
mm,
and get this meta network. And once we have this meta network, or for like meta parameters for these all these tasks, when at the classification you need to know what the task is. That's a tricky question. That's what we did this ITML paper. We don't know the task, but we only know the task. Uh, some sort of signal, we don't know the task. Hmm. I think it's depending on the setting we are like working on, but you need to have some sort of extra information for future learning, right? So like
future
support
learning.
set.
Yeah. So yeah, yeah. Anyway, that's interesting. So the yeah, probably I may have a Zoom meeting separately with you to learn more about
Yeah,
your work, and yeah,
yeah,
then
sure,
we
of
can
course, yeah.
yeah go for the some more projects. And so the I would like to personally thank actually Jathushan for
Nice.
actually
It's my
accepting our
pleasure to like back to you.
invitation,
It's
and I'm
even
also
it's
glad that
virtually,
you
but
are
it's good to back to
yeah,
uni.
you
Yes.
are one of my student, and so I'm really glad to hear a webinar of one of my students. So the I think the most of the participants are also one of my students. Yeah, my students. So the one day you will present similar webinars to the young generation, so you can take us yeah
Yeah, definitely.
motivation from yeah Yatsushan. And so we have a short vote of thank from the secretary of the IEEE Signal Processing Society Student Branch Chapter. So I would like to invite Miss Kitmini Hera to for the vote of thank. Kitmini,
Uh, yes.
yeah, we can hear you.
Okay. Uh, Hello. Good afternoon. Uh, First of all, it is a great honor for me to be delivering the vote of thanks today. I, on behalf of the IEEE Signal Processing Society Student Branch Chapter of University of Moratuwa, would like to thank Mr. Jathushan Rajasegaran for sparing us his valuable time. Thank you very much, sir, for enlightening us on how we can make use of continual learning to give systems the capability of remembering and dealing with past knowledge while learning from data continuously generated throughout the world. We consider it a great privilege to have attended this session and learned about some of the top research that's happening in AI. And I would like to extend my gratitude to Dr. Chamira Edusuriya, as always, for his immense support and guidance. Next, I would like to thank the executive committee and all who helped us in any capacity to make this event a success. And finally, thank you all for participating in this webinar. It has been a great pleasure. Thank you and have a nice day.
Yeah, thank you.
Yeah.
Thank you, Chitmini, and Jathushan. Again, thank you for your time, and so
Okay.
have a great day. And